you guys copied some of these notes yesterday, but just a reminder, there's two different things we can talk about. We can talk about polar bonds. We can talk about polar molecules. Based on electronegativity, recall that En values can be used to calculate whether atoms have partial positive charges or partial negative charges based on those bonds. All right. We're now going to apply that to the whole molecule. So the molecule as a whole, and that's ultimately what we need to do here and be able to do. So if we look at the shapes of molecular compounds, we can determine if the entire shape, the entire compound, or entire molecule is polar or non-polar based on these things here. We can use things like vectors, and we can predict whether they're polar or non-polar. And we can look at two examples here, water and carbon dioxide. Now, I don't know if we did this. I don't think we did this yesterday, did we? I think I just let you guys copy yesterday. So hopefully this is not too confusing for you here, but basically we look at carbon dioxide, for example. Okay, this bond between the carbon and oxygen. And we know from last day, lesson 11, we know that carbon is what, 2.6, I think? And this is a 3.4. And this is a 3.4 here as well. So if we consider the 3.4 to 2.6, where do electrons want to spend more time? Around this oxygen here or around the carbon here? Where do electrons spend more time? They spend more time around oxygen, right? So we know that the electrons are pulled towards oxygen, and of course that force there is 0.8 difference, yes? Okay? So they're pulled with a force of 0.8 towards the oxygen. It turns out that we have another carbon-to-oxygen bond right here. And once again, the difference between those two, of course, is 3.4 and 2.6, which is 0.8. And it's pulling this way with a force of 0.8. So when we look at this general molecule here, we see that basically there's an opposite pull on those electrons, right? Some are pulling this way, some are pulling that way. And those two forces, if you know about anything about vectors, of course, those two forces cancel each other out, right? So what happens to those electrons in this molecule? Are they pulled to a certain side of the molecule? And the answer is no. They're free to be shared equally amongst all these atoms here. Okay, it kind of goes back to this H to H thing, only this is a little bit more complex because we have, we don't have just one bond to worry about. We have two bonds. But those two bonds tend to cancel each other out in this particular case, yes? So what term do we want to use with this? Well, in this particular case, since those two forces are canceling each other out, electrons are shared equally. Of course, the term that goes with that would be nonpolar, yes? That is a nonpolar molecule, okay, because the two forces are in fact canceling each other out. Feel free to write some stuff down. Don't let me stop you. Nonpolar molecule. Now, the important thing to remember with this nonpolar molecule is we're talking, like I said, about two different things here. What kind of bonds does carbon dioxide have? It's got polar bonds, yes? If we look at this bond right here, that's polar, yes? It just so happens that that polar bond cancels out this polar bond to give you a nonpolar molecule. Yes? Okay? So that's really important here. So we end up with a nonpolar molecule. Nonpolar basically implies that there's not going to be a negative end and a positive end. All right? Then we come over to water here. Now this is going to be a little more tricky for you guys, perhaps, especially if you don't know anything about physics, aka physics. All right? And we look at these two here, and once again we use electronegativities. So this is what, 3.4, that's fine, 2.2, and 2.2. And you can already see we have some partial negatives and partial positives. But if we focus on just the bond between hydrogen and oxygen here, right here, this one, right? That's a polar bond, yes? H to O. That has a negative end to it and a positive end to it, right? Just right between here and here. And likewise, this one does as well. This one's got the negative end and positive end. Electrons get pulled closer to the oxygen here because it has the higher electronegativity, yes? The question becomes, though, do these two that are pulling up like this, on this angle here, do those two in fact cancel each other out, like they did on our previous example? And, of course, if you don't know anything about physics, well, there's a complicated way of figuring this out. here's one of the forces, that's this one right here, and this force here. And how do you add two vectors together? Well, you need to use parallelogram method, there's a triangle method, and there's probably a few different ways that I'm probably not familiar with because I don't like physics. Okay, but to add these two together, you make this dotted line here, and what you're doing is you're adding these two together here, the green one and the green one, and you get this one here. So the net result is that. Complicated? Possibly. It's okay. I'll make it easy for you. Okay? It's fine. This is not physics. This is chemistry. So we're okay. All right? Yes? All right. Nonetheless, this molecule, the forces do not cancel each other out. Okay? And therefore, we have a negative end, a general negative end at this end here. We have a negative end to the molecule. And yes, we have a positive end here and a positive end here, or generally speaking, this would be your positive end down here. Okay, and I'll show you the molecular model kit later as well, and we'll do that again with that. But it's got a general negative end to it and a general positive end. More specifically, yes, positive, positive, negative, yes? Okay, so we can't consider that one, since the two, we do have negative end and positive end, we consider that a polar molecule. So this one is polar. Water, turns out, is polar. And later on, we'll thank God for that. All right? Trust me. So it's polar. All right? So that's what we need to look at, the difference between these two molecules. And you need to decide which ones are polar and which ones are nonpolar. And that, of course, comes from the drawings and so on and so on. And if you're confused by this vector thing here, you don't have to worry about it because I've simplified it for you. First things first, though, before we simplify it any further, we know that symmetry is often going to help us determine which ones are polar or nonpolar. For example, CCl4. Okay, look. CCl4. Okay, when you look at that molecule, you know that there's a difference between C and Cl, yes? Cl is what? 2 or 4? Somebody look it up for me, please. Periodic table. Electronegativity. Quickly, quickly. Hurry. Somebody. Anyone. Help me out here. 3.2? 4? 3.2. 3.2 and this is 2.6. So do you agree there's a difference? Right? So this is a polar bond. That's a polar bond. That's a polar bond. That's a polar bond there. Maybe it's really cold. 2.6, 3.2. Electrons would get pulled this way, yes? That way, and that way. The question becomes, do all those forces cancel each other out? And the answer is yes, they do. How do I know? Because it tells you it's nonpolar. Yeah? So they all cancel each other out. But, for example, this one down here. If we change one of those, in other words, if it's not symmetrical anymore, see that one was nice and symmetrical, looked the same all the way around, yeah? This one, not the same all the way around. Are these forces all going to cancel each other out? And the answer is no. And if they don't all cancel each other out, we have a polar molecule in this case, and you know that because I told you that. So what are how are we going to be able to figure out which ones are polar, which ones are nonpolar? How can we summarize that for ourselves? And I guess part of it is, first of all, I think we need to talk about, well, I think we'll leave that as that, and we'll go on to the next slide here, and we'll talk about that, and then I'm going to show you some of the models with the model kit, and just explain something that's very crucial for you guys to understand here. So I think we're going to leave that as it is for right now. This is your summary of how you're going to know. Okay, this is the most important thing right here. Okay, and if you didn't finish copying this yesterday for some reason or whatever, make sure you do so today. Nonpolar molecules are possibly AX2, AX3, AX4 if the X's are all the same atom. Okay. Examples are CH4, BF3, CO2. AX2, AX3, AX4, but the X's have to be all the same. Okay? Go back to this one, for example, here. Right? Look. AX4, X's, Cl, 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 they're all the same. Nonpolar. Yes? Here is AX4. The X's are not all the same. Therefore, it is polar. Okay, yep. They're going to be probably very, very slightly polar. It honestly depends on which molecule we're talking about and the general shape. So that depends a lot on the shape, what we're talking about. Most of the time, phosphorus and arsenic won't combine together because they're kind of in the same group, right? So usually we don't talk about molecules like that. And it depends really ultimately on their shape is what it really depends on, and what else is bonded to it. Okay, so nonpolar molecules include AX2, AX3, AX4 only if X's are the same. If that's not the case, then we have polar molecules. Basically everything else not listed up here. So if it's not AX2, AX3, AX4, X's are the same, it's polar. If there's an E in the general formula, like for example, AX3E, automatically polar, no questions. AX2E2, tetrahedral bent, yes? 104.5, which you know for tomorrow. Polar, guaranteed. If there's any E in the formula, it's polar, all right? Now, we're going to take a look at, there's some questions here, and I'm going to give you time to do all those and stuff like that. But let's take a quick little, go to the last page. You got some room to write there, whatever. We're going to do a few examples together here. So, the first one here, CH4, okay? So tomorrow what you're going to do is the following for me on a quiz here, and I'll explain how the quiz is set up later, just to remind me. AX4, right? AX4. We know that this is tetrahedral. This is 109.5, and this is most certainly non-polar. Okay? I'm going to do all that stuff you need to know for tomorrow. Okay? And we'll do a little practice with the polar, non-polar thing, so don't freak out yet. You can freak out tomorrow. All right? Yeah, how do I want to do this? H. Well, let's say I'm going to do this one first, I guess. Okay? This one here. Okay? AX4, once again. Tetrahedral, obviously. 109.5. Is this one polar or non-polar according to our little definition about polar and non-polar? This one is most certainly polar. Okay? Are all the X's the same? Is the question. And in this case, they are not. Correct? So it's polar. Now, who looks at that and says, yeah, but really? Doesn't this cancel out this? True or not true? Not true. Why? I think I wrote it down here. Right? Remember, it's not 90 apart, right? They're not 90, 90, 90. It's 109, 109. This is three-dimensional. We're drawing it two-dimensionally. So now, let me show you. All right, just to reiterate my point here. Let's just quickly, here, we'll take a break here for this part. When you look at CH4, okay, you think, oh, well, let's figure out some electronegativities and go based on that. Now, and actually this is a good one to do because it's a little bit opposite of the ones we usually do. This is 2.2 here, yes? And this is 2.6. So which way are the electrons getting pulled between carbon and hydrogen? towards carbon, right? So we're getting a force this way, and this way, and this way, and this way. And do all those forces cancel each other out? And the answer is yes, because they're all the same force all the way around, right? Or vectors, or whatever you wish to use. They're all polar, but they're all canceling each other out. Okay, we can see that right here. Here's the dealio, though. Okay, it's not for the reason that you see up there. It's for this reason here. If you look at these two here, right? There's my carbon and hydrogens. Force is going this way, yes, into carbon and into carbon here, like this, right? What's the net result of this and this? Which way does the resultant vector, it's a fancy physics term, for those two forces, which way does it go? It goes down, okay, correct? If you're pushing on, for example, okay, somebody pushes here, somebody pushes here, what happens to this atom? It would go down, yes? Pushing down. So that goes down between these two. But then we look at these two bottom ones here, okay? So I hold it like this, and the force is going this way and this way, and what's the result of pushing like this and like this? Goes up, right? So the force down equals the force up, correct? Hence, nonpolar. Okay, that's truly what's happening here, not what you see here. This is too easy, okay? This and this, everybody knows that this and this is going to cancel each other out. What's really happening is three-dimensionally here, okay? Now you might say, you know, once again, what's the deal with this one? Well, you replace two of those atoms. I can make this complicated, or I can make this kind of easier for you. It doesn't really matter. It depends on how you want me to. I'm going to do easy first here. Now we put these two on, okay? And simply put, if you want to rearrange these letters, that's fine. I don't care, okay? But here's my two F's. They're the green ones. And there's my two H's. Those are the white ones, of course. Same thing. The question is this. If I'm actually going to do this one, by the way, I guess technically I'm just going to cheat a little bit here. I'm technically going to do this one, okay, first. And if you want me to rearrange them and do the other one, I'll do that one too. But let's look at this one for a second. And yeah, I left the lone pairs off here just for time-wise here. If you look at electronegativity, this is 4.0, this is 2.6, this is 2.2, this is 2.2, and this is 4.0. Let's look at these two. They get pulled that way, yes? True? They get pulled this way, yes? What about these ones? They actually get pulled this way and this way, right? Are those going to cancel? They actually add on to each other. Look, I'll show you. If you got electrons that are being pulled this way and this way, the net result of the green ones is up, yes? True? Now look at the bottom ones. We already talked about this. They go this way and this way. The net result is up, yes? So you're actually getting they're not canceling at all. In fact, all those vectors are adding together to give you a very, very negative end to the molecule, yes? Because everything's shoving that way, and a very positive end to the molecule, yes? So they don't cancel out at all. In fact, what I'm trying to get to you here is that this is a polar molecule, right? Now you might say, okay, well, what about not that one? Let's look at this one up here then. Okay, well, that's a little more complicated. Okay, now you're looking at this one, right? Between here and here kind of thing. Really, it's the same molecule, right? I mean, I can do this more complicated, but look, pulling this way and pushing that way. Oh, geez. Hey? The net result of that is kind of that way, actually. Believe it or not. Triangle method. That way. If you don't believe me, that's okay. The net result of these two here, once again, would be pulling that way. Okay? And once again, that's a little more complicated. But the thing is what I'm trying to get to is that even if you think it goes up and down, it doesn't in this case. They don't match up perfectly up and down. In fact, they add together in a way to make one end more negative, one end more positive. So once again, it is polar. Okay, and if you want to get into the math, then I can show you. But trust me, it's exact same. These are the same thing. Okay, so just so you guys know, it's three-dimensional, and the point is that if x's aren't all the same, it's going to be polar. Whether you looks like they cancel it or not, they don't. Okay, so let's do a few practice ones here, maybe. Well, let's just take a look here. Well, let's see. You know, once again, we talk about BH3 was one of the ones in your notes there for an example. Well, BH3 is boron, right? This is the exception. You only need to have 6 electrons around it, or boron only needs 3 electrons, or a pair of 6, right? This is trigonoplanar. This is 120 and non-polar. AX3, yes, okay. So AX3 can be non-polar if x's are all the same. So if x's are all the same, it is non-polar. Remember, if you got a tug-of-war here and these are all the same angles, who's going to win? And the answer is no one. In fact, I can do that with that one because remember, trigonoplanar means that they all line up on the same plane, right? They're all on a plane, so they make a perfect 360. They're not three-dimensional. This one's not. And if you're pulling with forces of, you know, between 120, 120, 120, if you're pulling with the same force, they're all going to cancel out. Okay? So that's a non-polar one. Obviously, CO2, right? We talked about that one before. Those two cancel out. Symmetrical, right? X's are the same. If you go to draw, for example, NH3, okay? Right away, when I look at that molecule, I can tell you right now, without doing any other work, just by drawing it, that that is most certainly going to be polar, because it has a lone pair on the central atom. AX3E, trigonal, pyramidal. Make sure you know all the names for tomorrow. 107.3. This is most certainly polar because it's got an E in the formula, right? Look at, you know, here's your example of nitrogen trihydride or ammonia right here. Okay, look. You know, once again, we have to talk about symmetry. Does it look all the same all around? Well, it's good here, but then we got this lone pair on top. We don't know lone pair stuff. It doesn't have the same electronegativity as anything else here. In fact, the net result of this, when you look at nitrogen trihydride, I would think that the electrons are going this way, and this way, and this way. So the net result would be kind of up towards this nitrogen here, or up. And then you got a lone pair stuck on top. And we'll talk about how lone pair affect the structure as well. Like obviously it bends stuff away farther from it, right? Pair repulsion theory. But it also enhances the negativity of the nitrogen as well. Okay? So it actually just builds on it. So, you know, once again, most certainly polar. It has to be symmetrical. And the only time you're going to have symmetry is if it's AX2, AX3, AX4, all the x's have to be the same, non-polar. Everything else is polar. And if you get stuck on the quiz tomorrow, I guess what I'm trying to say to you is probably guess polar, I guess, because most of the stuff's polar. Okay? All right? Does that make sense? So I'm going to give you guys some work here, some practice, and then we're going to go over these in about 20 minutes or so. You got some things to draw out here. You need to practice drawing these. Okay? What do you need to do with these? Well, they're right on the page before here. You're going to draw it out, as always. This is going to be your quiz tomorrow. Here's how the quiz is set up. You're going to have 30 or 35 blanks to fill in tomorrow. It's going to be set up in a table format. I'm going to give you either the name, so sulfur difluoride, or the formula, and you're going to draw it in one of the squares. It's like a table. It's a big table. Draw it. You're going to tell me the formula. You're going to tell me the name of that shape, basically, trigonal, pyramidal, tetrahedral. State the bond angle, and then finally in the last column, polar, nonpolar. That's what you're doing for at least 6 or 7 compounds, so that gives you your 30 or 35 blanks that you need to fill in. Okay, do you understand? So you're going to practice that right now. Those are the 5 things I want for each one of these, and these are the compounds that you're going to do. Now listen, before you start, one more thing. Look, I get it. Tomorrow I'm not going to ask these. I'm going to keep them fairly straightforward, okay? Having said that, you need to start applying this a little bit more than just what we've been doing. So these are all good. When you get to this one here, that one's going to be a little bit tricky. It may not have a general formula for you to fill in. It might not have a general shape. And that's okay. If you want to leave that blank for today, that's fine. I'm not going to ask you that on the quiz tomorrow, but I want you to draw out H2O2, which is something you should be able to do. And if you look at it, I want you to tell me, is it polar or nonpolar? That's something else you should be able to do. Okay? And the other tricky one is going to be this one here, because there's only 2 atoms. And if there's only 2 atoms, what's the general formula going to be for HCl? I don't know, because there's only 2 atoms. If it was 3, I could tell you it's AX2, but there's not. So bond angle doesn't apply. Name of that shape, well, you could probably come up with a shape name for that one. You could, after you draw it, you'll see. But still, you should be able to tell me if it's polar or nonpolar, okay, ultimately, by looking at it. Okay, so I'll let you guys work on those, and then we'll go over those in a bit here. Quickly, CH3F, okay, drawing, yes, that's not enough. No, it is, yeah. CH3F, that one, of course, is most certainly AX4, tetrahedral. This is 109.5, and most certainly polar, okay, because all the X's are not the same. CH2F, or CH2O, we've done this one before, so if you need a little help with these, then once again, this is the most important part, because if you can't draw them, you're not going to get the right formula, right? And that's going to, if you get this part wrong, then guess what? The formula's wrong, the name's wrong, the bond angle's wrong, and there's a chance the polar, nonpolar thing's going to be wrong. I don't give you part marks, so that row tomorrow is going to be completely wrong. And I have to, because I don't have an option, okay? You can't mess this up, because it's going to affect later on. This is AX3. This is trigonal planar. This is 121, 121, and 118, right? Because double bond, yes, AX3, double bond, more pairs of electrons, pushing a little bit more. So that opens this up slightly, which means that has to shrink. Regardless, whether that's the case or not, you don't have all the same X's here, so this is most certainly, once again, a polar molecule. Okay? Yep. I can come check later. Yeah. That's fine. You can turn this or whatever. If it's not all spread out exactly like that, that's ultimately okay. You're still important. You know, we should be trying to spread some stuff out, though, right? I mean, that's the... Yeah, that's fine. Electron pair repulsion, all right? ASI3, ASI3 looks like this. Right away, I see that, right? AX3E, this is trigonal pyramidal. 107.3, and this is most certainly polar, because anything with an E in it is polar, okay? So that's that one there. Which one is next here? H2O2. So this one's a little bit tricky here. The important thing is, remember how we drew, you know, we looked at oxygen, and I told you guys, make sure you draw the 6, 1, 2, 3, 4, and then start pairing up 5, 6, right? Because that's what oxygen looks like, and I'll show you this. I'll make the model later for you. So this has to hook up here, this has to be the H, and that has to be the H there. Remember, oxygen, you know, think about water. What does water have? It's that tetrahedral bend shape to it, yeah? So when you look at this one, you might say, well, how am I going to name this? What's the general formula? There is no general formula for this one. There's no name for this one. But we did take some notes that said, if you look at this part right there, that's tetrahedral bent to that part, yes? Okay? And then I said, if you look at bigger molecules, you may have to split this into two sections. Some of you would say, you know, that's tetrahedral bent there. So you can kind of break it up into two sections. Am I going to ask you this tomorrow? No. Okay. Will you get this molecule sometime, maybe down the road? Perhaps. When you look at that, you should be able to tell me if it's going to be polar or non-polar, though. And I would hope that you would pick probably polar, right? Because forces are not going to cancel each other out there. It's not symmetrical all the way around. Remember, lone pairs, anything with lone pairs is probably going to be polar, right? So this turns out to be a polar molecule here. Looks kind of like a PlayStation. Chem Guy 243, yep. And Chem Guy 243 starts talking to you, don't talk back. What is it, BH3 is next? No, what's next? BH3. Okay, AX3, trigonal planar, 120. This is the perfect 120, and of course nonpolar. Now, you'll quickly understand that AX3 ones, right? If we're talking about boron in the middle, that's probably the only ones for AX3 that are going to be nonpolar. Because if you go back to the other AX3 ones we've had double bonds in them. Boron's the exception, it allows 6 around it. So this is the perfect 120, 120, 120. And in fact, those are the only types of molecules, AX3 molecules, that can be nonpolar. Because anything else, as far as AX3 goes, will have double bonds in it to make the octet, yes? Okay, so just kind of keep that in mind, that really boron type molecules are the only ones that can be probably nonpolar all the way around. Yeah? So that's nonpolar. What's the next one? CH4, okay, another, we did this one before. Tetrahedral bent, or sorry, tetrahedral, AX4, right? AX4, tetrahedral, 109.5, nonpolar. Okay, for that one there, we've done that one quite a few times now, so that's a nonpolar one. Next we have SO3. This one here, I'm going to tell you, like, anytime you have S and O's combined together, those are tricky ones. You almost always have to SO2, SO3. This one is just SO3, by the way. This is not SO3 2 minus. All right, I didn't forget the 2 minus on there. This is just SO3. These are tricky because usually you have to, when you get a combination of S's and O's, you have to add them up. Okay, that's a total of 24 electrons. All right, 1, 2, 3, 4, 5, 6, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. You've used all 24. If this was SO3 2 minus, you just put the other 2 at the top there, you'd be done, right? Don't forget the brackets and the charge. I might ask you to do one of those tomorrow. We did some practice with that the other day here in lesson 11. This one here, you have to move a pair in, yes? So you'll end up with something like this here. Okay, SO3. Now, this one's a little bit tricky, okay? This one is AX3. This is trigonal planar. 121, 121, and 118. Don't forget, okay, because of the double bond there. So even though, and this is kind of probably one of the exceptions, and like we were talking, I'm probably not going to ask you this one because this is a bit, you know, there's a few problems with this one as far as Chem 20 goes. But if I ask you this one, I would probably say this has to be polar at this current time. Because even though we have AX3, and I don't care about the double bond, or what's, you know, the bonds, we have to look at what are the angles, are the forces going to cancel each other out in this big scheme of things. And because the bond angles aren't exactly 120, 120 and 120, they're off a little bit. They're going to be, of course, they're not going to cancel each other out. Okay, so I would probably tend to believe that this one's going to be polar for our purposes. Once again, I won't ask you that one. And then you get into things like resonance structures and all this other stuff that creates habits and that kind of stuff. So you'll figure that out some other day. All right, I won't ask you that one. HCl. Okay, now listen. This is a simple molecule, right? You know, we look at this one. What's the general formula of HCl? The answer is I don't know. We don't have a general formula for this one. The smallest one we have is AX2. This is AX, I guess, and I don't even know what the central atom is because they're both technically got one electron, paired electron, right? So this is just a 2-atom molecule here, which is fine. I wouldn't say it's AX2 or anything like that. I would probably say that this has a linear shape to it. Yes, roughly, right? I mean, it's not stretched out by any means, but it's kind of linear-ish that you have there. It's definitely got a negative end and a positive, and how do I know that? Because there's a difference in electronegativity. Just turns out that there's only one bond here. So due to this one bond here, I would tend to believe that this has a negative end to this molecule and a positive end to it, and therefore I would say that this is a polar bond. Turns out it's the only bond in this molecule, so it's a polar molecule as well in this particular example. All right. Ultimately, the question is, you know, is there any other force to cancel this one out? And the answer is no. We've got H to Cl. There's a difference in electronegativity. It's going to be not only a polar bond, but that's the molecule as well. It's a polar molecule. It's got a negative end and a positive. So it's most certainly polar. I don't have a name for that. I don't have really a general formula. Like I said, if I had to name it, I'd probably say it's linear-ish, right? But other than that, that's pretty much all I can tell you. pH3, you know, very common one here, of course. We look at this, we say this is AX3E. This is trigonal pyramidal again. This is 107.3, and most certainly polar, as it has a lone pair on the central atom. Next is what, H2O. As always, water. Most certainly polar. We go AX2E2, R2D2, D3PO. Trekkies, right? This is called tetrahedral bent, 104.5. Okay, and most certainly, obviously, polar. Okay, lone pairs on central atom. You know, once again, we can't talk about lone pairs canceling out lone pairs. That's not going to happen. Okay, we need to talk about, like I said, we'll probably, if anything, like no electronegativity in both pairs. SBR2, same thing. Okay, SBR2. AX2E2, tetrahedral bent, polar, 104.5 again, all the same stuff we just had for the last one. Yes? Okay? And then that's pretty much it for those drawings. Okay? Make sure you study the 6 names. There's 6 different shapes. I don't know how many we did up here, I don't remember. Okay? I can tell you one thing, I'm pretty sure we didn't cover all 6 shapes. Nudge, nudge, wink, wink. So, I'm pretty sure that that wasn't the case. So make sure you study all 6 shapes, all the bond angles, the names, etc., etc. Get some practice with those. This way, we're not done yet. Don't worry. 10 minutes left. Last one, NF3 and NCl. Okay, stop backing up. I don't know where you're going. Okay, which one's more polar? Well, once again, you have to think about the general. These are obviously both polar. Which one's more polar? Well, this one has electronegativity of 4.0. This is 3.2. So if you think about the two shapes that we have here, which I probably don't have any more here, no. But remember, the NF3 one has the 3 coming out at the bottom, 1, 2, 3, and then the lone pair sticking up. The net force here, if you're dealing with 4.0s, 4.0 and 4.0, pulling this way and that way kind of thing, is going to be down. Now, I don't know what that force is exactly. You have to do a little bit of fancy math, but it's going to be down. Okay. This one here is exactly the same shape, but the fact is you got 3.2 and 3.2 and 3.2, so the forces aren't as big. So this one is probably going to be slightly less down. Okay. So which one is going to have a more polar end to it? Which one's going to be more polar? It's going to be the NF3 one. Okay. A bigger difference in electronegativity usually leads you to a more polar molecule. Okay. Usually. Now, there's some exceptions to that, of course, but usually that's the case. All right. Okay. So I think that's it for that.